Okay, so this is 8.1, and this is a very vocab-focused assignment. And so really this is about us getting the basics down so that we can make more significant moves in 8.2 through 8.5. We're going to do what's called hypothesis testing, and we're going to start that process today. We really won't get through a hypothesis test, but we want to know how they're built, and we'll start the step one, basically, of doing a hypothesis test. So you can read here, researchers are often interested in asking and answering, questions like, is the earth warming up? Does new medication lower blood pressure? Does the public prefer a certain color of a new fashion line? Do seatbelts reduce the severity of injuries? These questions, saying that it helped, like that a blood pressure medication lowers people's blood pressure, like how do we know it does? And to what level are you willing to guarantee that it's going to work? Is it just a coincidence that you picked people who their blood pressure was kind of going down anyway? Or how do we know that this is true? And so this hypothesis test allows us to mathematically validate whether something is true or false that we may have claimed. There are three methods to use for the hypothesis tests. We can do a traditional method, which is what we're going to talk about first. Another day we'll talk about p-value method, and we'll talk about the confidence interval method. Traditionally, when we talk about a statistical hypothesis, it's a conjecture or statement about a population parameter, about the mean, or about the standard deviation, or about something along those lines, the proportion. It may or may not be true. The null hypothesis, which this is not symbolized right, it should be written symbolized H with a subscript 0. The null hypothesis is a statistical hypothesis that states there is no difference between a parameter and the specific value. So the parameter that we're going to use first would be the mean, and here we would say that the mean is equal to a specific number based on previous data. We'd say, hey, we think that the mean is not different. So the null hypothesis is that there is no difference, or that it's exactly equal. The alternative hypothesis, which is symbolized by H sub 1, okay, is going to be that there is a difference. Okay, it could be that mu is not equal to a specific number, or maybe on a different one, you could have an alternative hypothesis that says mu is greater than some number. You could also have an alternative hypothesis that says mu is less than some number. So the alternative hypothesis is us making a claim that whatever the parameter is, or whatever we think the parameter was, it's not that. Could be less than, greater than, or not equal to. We would pick one of those based on the problem. Some examples of this, medical researchers interested in finding out whether new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after the patient takes the medication? The researcher knows the mean pulse rate for the population under the study is 82 beats per minute. So the null hypothesis here is going to be that the mean is 82 and that this medication will make no difference. Because the person's interested in increase or decrease being a concern, we're going to say that the mean for the alternate hypothesis would be that it's not 82. If he was only worried about being greater than 82, we would do just greater than 82. If we worry about it dropping people's pulse rate, then we would worry about the less than side. When it's a not equal to, okay, when we get this not equal to, it's called a two-tailed test. Another example, a chemist invents an additive to increase the life of an automobile battery. The mean lifetime of an automobile battery without the additive is 36 months. So you can see that the null hypothesis is that mu is 36. We always do the null hypothesis as the equal sign. But he thinks it will increase the likelihood or the life of the battery, which means we're going to do the greater than, that it will be bigger now. And because that arrow is pointing to the right, this is a right-tailed test. If I did a less than problem, that less than would make it a left-tailed test. When we make these two statements, okay, about our hypotheses, one of them is going to be listed as the claim, the thing that we're trying to get evidence to support. So here, the researcher may say, I don't think this medication is going to affect the person's heart rate, and so I'm going to claim that the null hypothesis is true. That's maybe an example of making a claim. Down here, this person wants to prove that it makes the batteries better. So the claim would be the alternative hypothesis. We always want to pick a claim that we're trying to back up. Typically, that claim is the alternative hypothesis, or what sometimes is called the research hypothesis. However, if we wanted to, we could use the claim as the null hypothesis, but we have to remember is that we can reject or fail to reject the null hypothesis. The language in this is going to get a little wordy, and you'll see a better explanation of it as we get into examples in 8.2 and 8.3 and so on. The wording of what we do with our test at the end, the conclusion, is really important. So knowing where we pick our claim, what we're trying to validate in our claim, we pick the one that we're trying to prove is true, and then we're going to make specific statements about what the research tells us. After we state the hypothesis, the next step is to design the study. The researcher selects the correct statistical test for a mean. In this first section, we're going to do a z table, and we find the appropriate level of significance. Okay. The statistical test is going to compare the critical value with the test value. You can read through these. It's really, until we start getting into it, it's a little bit tough to understand. But here's the issues that come up. If you can think about drawing a bell curve, okay, and let's say that I want 90% confidence level, okay, which means my error over here is going to be 5% on a side. All right. If I think the mean is, say, 30, and say this cut value is something like 35, it's possible that I would get a sample, and my sample would have a mean of 36. If it's over here in this region over here, I would reject the null hypothesis, say the average can't be 30 because I'm way out here on the extreme end. The problem is maybe I just got bad data. Like I gathered data from a biased group, and so really the mean is 30, but I had too extreme of a value. This is what's called a type 1 error. When we reject the null hypothesis, we say, it can't equal 30. But if I had taken a different sample or a bigger sample, I'd learn it actually is 30. Okay? So that's type 1 error. We reject the null hypothesis when we shouldn't. The other type is maybe I make my region over here really small. Maybe I go to 99%, and I end up keeping the null hypothesis, not rejecting it when I should, because I made the region so wide in the middle that I made it almost impossible to reject the null hypothesis. Those are a couple of things we worry about. It's like the concept of a false positive or a false negative. Those kinds of is it really true, is it not true? Sometimes we reject things when we shouldn't because of the level of significance we choose. The probability of a type 1 error is known as alpha. That is our tail out here. 5% here, 5% here. That would be a 10% or 0.1 level of significance. So our levels of significance are usually 10%, 5%, and 1%, and we do them as one tail or two tail tests. Critical value is the line in the sand that separates the middle bubble, where we do nothing, and the extreme edges, where we would reject our null hypothesis. The critical rejection region is that region out on the edge, and the non-critical region is the area in the middle. So again, if you think about your bell curve, we kind of dealt with this a little bit, but if I have a cut value right here, let's say it's a right tail only test, okay, this is non-critical, but this area over here would be critical. And anything over here, if you land over here, you'll reject the null hypothesis. If you land in the non-shaded area, you're not going to reject your null hypothesis. If you need to know the critical value for different alpha values, what I will always do is I'll draw a diagram of the area, kind of figure out what's the area over here, If it's 0.01 to the right, that means it's 0.99 to the left. You're going to go to your z table, which we've done, and you're going to go looking for that 0.99. Okay? We want the closest value to 0.99. If there are two that are equally spaced, you would pick the smaller of the two. But you can find that the z value is now 2.33. That would be my z value. So let's do the critical value for 0.01 if it's a two-tailed test. At 0.01, because it's two-tailed, I have to cut it in half, which means I'm looking for 0.005 on the left or 0.005 on the right. Because of symmetry, if I go back to chapter 7, grab my z table, I'm just looking for 0.005. I'm going to look here in my negative side, because it's a little easier to find the 0.005. 0.005. Okay, I've got these two values here, and I'm going to always go to the smaller of the two. So I'm going to go to 0.08. If I slide over, that's negative 2.5. So that tells me that in my z-score, okay, the z-score for this is going to be negative 2.58 for the left, and over here on the right, a positive 2.58. Those would be the z-scores that would cut my graph. Okay, and any number of z that you get that's beyond those would be big enough or extreme enough to cancel them. This is the traditional method. We will go through this more in future assignments, but you just need to constantly have this with you. State your hypotheses and identify a claim. Find the critical values that cut your graph. Compute your test value for your specific data, and then make decisions to reject or not reject the null hypothesis and summarize the results. This is going to make a lot more sense when we actually go through some examples in future sections. Today you need to know how to find the z values, which you should already know how to do, and you need to know how to create the null and alternative hypotheses. Good luck, and we'll see you in class.